viewers, welcome to CEC Gurukul online lectures. In today's lecture, we shall be discussing preparation of alkyl halides from alcohols. The reaction of an alcohol with an halide anion is an example of nucleophilic substitution reactions. As you know, carbon atom in alcohols is attached to a more electronegative oxygen of the hydroxyl group. That is, the functional group in alcohols is OH group, and the carbon containing the OH group is attached to more electronegative oxygen. As a result of which, oxygen, being more electronegative than carbon, pulls the electrons towards itself, as a result of which carbon has a partial positive charge and it undergoes nucleophilic substitution reactions. It undergoes a substitution reaction because alcohols are saturated in nature. A halogen atom, usually chlorine or bromine, replaces hydroxyl group attached to carbon, resulting in the formation of alkyl halide. Common methods used for converting alcohols into alkyl halides are reactions of alcohols with halogen acids like HBr, HCl, Hi, resulting in the formation of alkyl bromides, alkyl chlorides, and alkyl iodides. Alcohols can even react with phosphorus halides like phosphorus trichloride, phosphorus tribromide, or phosphorus triiodide, which is prepared in situ by reaction of phosphorus with iodine, resulting in the formations of chlorides, bromides, and iodides. A very good method for preparation of alkyl chlorides is by reaction of alcohols with thionyl chloride. Now I have shown on your screens a general reaction in which an alcohol is reacting with HCl, resulting in the formation of alkyl halide and a water molecule. This reaction seems to be very simple, but it is not as simple as it seems, since OH is a strong base and it cannot be substituted easily. That is, the bond between the carbon and between the sp3 hybridized carbon and the sp3 hybridized oxygen is a strong bond, and OH cannot be replaced easily. So now I have shown on your screens another reaction in which I have shown that methanol is reacting with a bromide ion, with the result that no reaction takes place, since bromide anion is a weaker base as compared to hydroxyl group. It cannot replace it. So in order to bring about nucleophilic substitution reactions in alcohols, we will have to convert this OH group into a good leaving group. That is, we will have to convert a strong base into a weak base. One way to convert OH into a good leaving group is by doing its protonation. Protonation changes the leaving group from OH, a strong base, to water, a weak base, which is weak enough to be displayed by a nucleophile. Sometimes the substitution reactions are slow, and in order that they take place at a reasonable time or at a reasonable speed, we need to heat the reaction mixture. Here again you can see on your screen the reaction of methanol with HBr. In this reaction, first methanol undergoes protonation, and then on heating, the OH group is converted into a good leaving group and it is eliminated as water molecule, resulting in the formation of methyl bromide. Since the OH group of alcohol has to be protonated before it can be displaced by a nucleophile, only weakly basic nucleophiles can be used in the substitution reaction. As most good nucleophiles are basic, they become protonated and lose their nucleophilicity in acidic solution. Let us look into the example of ammonia. If we use ammonia as a nucleophile in acidic conditions, then ammonia undergoes protonation and is converted to ammonium ion. In ammonium ion, nitrogen has positive charge on it and it fails to react as a nucleophile. Halides are anions of strong acids, so they are weak bases. Solutions of HBr, HI or HCl contain nucleophilic bromide, iodide or chloride ions in solution. These acids are commonly used to convert alcohols to corresponding alkyl halides since the nucleophiles are weakly basic and would not undergo protonation under acidic conditions. Let us now look into the reactivity of halogen acids, and what we find is that the order of reactivity of halogen acids parallels their acidity. That is, HI is most reactive since the bond length between hydrogen and iodine is long, and since it has a long bond length, it will have low dissociation energy and it will dissociate easily to give us protons, which will then help in bringing about protonation of the OH group. Secondly, what we find is that the order of nucleophilicity of these bases is also iodide, greater than bromide, greater than chloride. Reason being that the iodide atom is larger in size and therefore the negative charge, or it is more polarized and it can act as a better nucleophile. If we look into the order of reactivity of alcohols, we find that tertiary alcohols are most reactive, followed by secondary alcohols and then the primary alcohols. This order of reactivity can be explained on the basis of stability of carbocations which are formed as intermediates in some reactions. The tertiary carbocation is most stable, as I have shown you on the screen. In tertiary carbocation, the carbon bearing the positive charge is attached to 3 alkyl groups, and in this case we've seen the example of tertiary butyl cation in which carbon is attached to 3 methyl groups. In isopropyl cation, it is attached to 2 methyl groups. In ethyl cation, it is attached to 1 methyl group, whereas in methyl cation, it is not attached to any other alkyl group. The tertiary butyl cation is most stable since it is attached to 3 methyl groups which have a plus I effect, which will show hyperconjugative effect. As a result of both these effects, the positive charge on the carbon will be decreased and it will be most stable. Hence, tertiary alcohols will form carbocations most easily and they are most reactive towards reactions with hydrohalogen acids. Now let us look into these reactions one by one. First, let us look into the reaction of alcohols with hydrobromic acid. Concentrated hydrobromic acid rapidly converts tertiary butyl alcohol to tertiary butyl bromide. The mechanism, if we look into the mechanism, it consists of 3 steps. In the first step, there is protonation of the OH group. That is, the lone pair of electrons on oxygen will react with the proton from HBr in an acid-base reaction, resulting in the formation of tertiary butyl oxonium ion. Now this tertiary butyl oxonium ion loses its OH group in form of water molecule, resulting in formation of a tertiary butyl carbocation. So during protonation, we have converted OH, which is a poor leaving group, into H2O, which is a good leaving group. Now this tertiary carbocation reacts with a bromide anion, which acts as a nucleophile, resulting in the formation of tertiary butyl bromide. Now if we look into this reaction from the structural perspective, what we find that carbocations act as strong electrophiles, since in them the carbon has a positive charge and it has an empty p orbital, whereas halide, which is acting as a nucleophile, is complementary in structure to electrophile. That is, its sp3 hybridized orbital has non-bonding electron pair, which forms a bond with the empty p orbital of the carbocation, resulting in the formation of alkyl halide. Secondary alcohols also undergo SN reactions with HBr by a similar mechanism. That is, in them, if we take an example of cyclohexanol, which is a secondary alcohol, then it also reacts with HBr, resulting in a formation of carbocation, which then reacts with bromide ion, resulting in formation of bromocyclohexane. So in this case also, the first step is the protonation of the OH group, which is then eliminated as water molecule, resulting in the formation of secondary carbocation, which then reacts with Br- to form bromocyclohexane. Primary alcohols react with HBr in different reaction mechanisms. What we've discussed till now is the mechanism of tertiary alcohols with HBr. So when we talk of a tertiary alcohol, then the reaction mechanism is SN1. And when we talk of primary alcohols, then the reaction mechanism would be SN2. SN1 is a unimolecular substitution reaction, whereas SN2 is a bimolecular nucleophilic substitution reactions. I shall be discussing the mechanism of these reactions in great detail in my subsequent lectures on nucleophilic substitution reactions. So as I was talking of primary alcohols, what we find that the structure of primary alcohol is very different from a tertiary alcohol. In primary alcohol, the carbon containing the OH group is attached to one other carbon. Therefore, when it dissociates, it will form a primary carbocation. And we know that primary carbocations are unstable and too high in energy to be intermediates in nucleophilic substitution reactions. That is, they will not follow SN1 mechanism. they will react slowly by an alternative mechanism, which is an SN2 mechanism. So what happens during the course of reaction? Here in the first step, the protonation of the alcohol takes place. And in the second step, the difference arises. So what we observe here in the second step, that the carbon halogen bond begins to form before the carbon oxygen bond of the alkyl oxonium ion is completely broken. Thus, carbocation intermediates are not formed in the reaction. The halide nucleophile also helps to push off a water molecule from alkyl oxonium ion. So in the first step, as you can see on the screens, we've already shown that the first step has taken place and the primary alcohol has undergone protonation to form primary alkyl oxonium ion. Now, the halide anion attacks the carbon which is bearing the OH group from the opposite side, and a transition state is formed in which there is partial bond formation between the halogen atom and the carbon, and the bond is being cleaved between the carbon and the oxygen atom. Now this halide being a stronger base as compared to the leaving group, it will push out OH as water molecule, resulting in the formation of primary alkyl halide. I have demonstrated or illustrated this reaction by taking an example of butane 1-ol. When butane 1-ol reacts with sodium bromide in concentrated sulfuric acid, it gives bromobutane by a SN2 mechanism. In this, sodium bromide reacts with sulfuric acid to generate HBr in solution, and this hydrobromic acid then brings about, or it reacts with 1-butanol and converts it to 1-bromobutane in 90% yield. As you can see on your screens, 1-butanol reacts with HBr, and in this case, the first lone pair of electrons on oxygen pick up a proton from HBr, resulting in protonation of the OH group. In next step, this OH group, the bromide ion will attack from the opposite side, since this is a primary alcohol and there is no steric hindrance in it. And we get a transition state in which bond is being formed between carbon and the bromide anion, and the bond is being cleaved between carbon and the oxygen atom. The bromide anion helps in pushing out the OH group as water molecule from the transition state, resulting in the formation of 1-bromobutane. Now we shall be concentrating on the reactions of alcohols with hydrochloric acid. Hydrochloric acid reacts with tertiary alcohols like hydrobromic acid. For example, concentrated aqueous HCl reacts with tertiary butyl alcohol to give tertiary butyl chloride in a similar manner in which HBr reacts with tertiary butyl alcohol. That is, the reaction will be accompanied by formation of carbocation intermediate. That is, reaction will follow SN1 mechanism. As you can see, a tertiary butyl alcohol reacts with HCl, resulting in formation of tertiary butyl chloride in 99% yield. Chloride is a weaker nucleophile than bromide ion because it is smaller and less polarizable. Therefore, reactions of secondary and primary alcohols cannot be carried out only with HCl. An additional Lewis acid such as zinc chloride is necessary to promote the reaction of HCl with primary and secondary alcohols, since zinc chloride is a strong Lewis acid. Zinc chloride coordinates more strongly with the oxygen of the alcohol in the same way as proton does. Here I have shown the reaction of 1-butanol with HCl in presence of zinc chloride when 1-chlorobutane is formed. In the first step, the reaction 1-butanol reacts with zinc chloride, resulting in a transition state. In the transition state, as we can see, there is partial bond formation between the chlorine and the carbon and partial bond cleavage between the carbon and the oxygen atom. And chloride ion, being a stronger nucleophile as compared to the leaving group, it pushes out the leaving group as OHZnCl2, resulting in the formation of the product, which is 1-chlorobutane. Now let us look into the limitations of hydrochloric acids with alcohols. Alcohols on reaction with hydrohalic acids do not always give good yields of the expected alkyl halides. This is because of the 4 limitations that it has. First of all, we get a poor yield of alkyl chlorides from primary and secondary alcohols. Primary and secondary alcohols react slowly even with HCl in presence of zinc chloride because the reaction is slow. So these reactions undergo side reactions, as a result of which the yield of alkyl halides is not very good. That is, the yield of alkyl chlorides is not very good. Second, these reactions may be accompanied by eliminations also. When we heat an alcohol with concentrated acid, such as hydrochloric acid or hydrobromic acid, it often leads to elimination. Once the hydroxyl group of alcohol has been protonated and converted to a good leaving group, it becomes a candidate for both substitution and elimination. What we mean here is that once the alcohol has undergone protonation, then the possibility is that the halide ion may displace the good leaving group, resulting in the formation of a substituted product, or a proton may be removed from the carbon which is adjacent to the carbon from which the leaving group has been removed, resulting in the formation of an eliminated product. Third, what we find is that there is limited ability to make alkyl iodides by reaction of an alcohol with HI, because many alcohols do not react with HI to give us high yields of alkyl iodides. Iodides can be prepared by an alternate method, that is Finkelstein reaction. In this reaction, alkyl bromides are treated with sodium iodide in acetone when alkyl bromides are converted to alkyl iodides, and this is an example of ion exchange reaction. The last point, which is very important, is the rearrangement reactions. We know that carbocations are formed as intermediates when a tertiary alcohol or even a secondary alcohol reacts with a hydrogen bromide or hydrogen chloride, resulting in formation of carbocations. If a tertiary carbocation is formed, the reaction goes on. That is, that tertiary carbocation will react with the halide ion to give us the product. But if primary or secondary carbocations are formed, then they have a tendency to rearrange to form more stable carbocations by 1-2 shifts. These shifts could be through hydride shift or through an alkyl shift, resulting in more stable carbocations, which then react with the halide ion to give us the product. So we do not get the desired product. For this, I have illustrated with an example of reaction of 3-methyl butane 2-ol with HBr. Carbocation rearrangement reactions can be explained by taking an example of reaction of 2-methyl-2-butanol with concentrated HBr. In first step, 3-methyl-2-butanol undergoes protonation, resulting in the formation of oxonium ion. This oxonium ion expels a water molecule, resulting in the formation of secondary carbocation. This secondary carbocation converts into tertiary carbocation by 1,2 hydride shift, because tertiary carbocation is more stable as compared to secondary carbocation, and the major product formed is reaction of the tertiary carbocation, that is 2-methylbutane with bromide anion, resulting in 2-bromo-2-methylbutane, and 2-bromo-3-methylbutane is the minor product. Now, if we have to prepare primary and secondary alcohols, then we can bring about the reactions with phosphorus halides. Phosphorus halides produce good yields of most primary and secondary alkyl halides. The phosphorus halides which can be used to bring about halogenation are PbR3, Pi3, PCl3. The two phosphorus halides used most often are PbR3 and phosphorus and iodine in combination. Phosphorus tribromide is often the best reagent for converting a primary or a secondary alcohol to alkyl bromide, especially if the alcohol might undergo rearrangement in strong acids. That is, if we want to convert neopentyl alcohol to neopentyl bromide, then we should carry out the reaction of neopentyl alcohol with PbR3 rather than carrying out the reaction with HBr. Because if we will carry out the reaction with HBr, the neopentyl carbocation formed will undergo rearrangement to form a tertiary carbocation, which will then react with bromide ion, and we will not get the desired product. A phosphorus and iodine combination is one of the best reagents for converting a primary or a secondary alcohol to an alkyl halide. Phosphorus triiodide is not sufficiently stable to be stored, therefore it must be prepared in situ. That is, it should be prepared in the reaction mixture by reaction between phosphorus and iodine when phosphorus triiodide is formed. And now this phosphorus triiodide reacts with alcohols to form alkyl iodides. Here I have shown few reactions of alcohols with phosphorus, tribromide and phosphorus and iodine. In first reaction, neopentyl alcohol is being converted into neopentyl bromide, and please remember, as I have already discussed, in these reactions we should not bring about the reaction with HBr because it will undergo rearrangement and not give us the desired product, which is neopentyl bromide. In the second reaction, we have shown the reaction of a primary alcohol with phosphorus and iodine when we get a alkyl halide iodide in 85% yield. Phosphorus tribromides react with alcohols to give alkyl bromides and phosphoric acid. As you can see on your screens, the general reaction, that is 3 molecules of alcohols, reacts with 1 molecule of PBr3, resulting in formation of an alkyl bromide. And for this, we can take a reaction of isobutyl alcohol with phosphorus tribromide, resulting in formation of isopropyl bromide in 55 to 60% yield. If we look into the mechanism, then what we find that PBr3 is a strong electrophile and alcohol displaces bromide ion from PBr3 to give an excellent leaving group. The bromide ion displaces the leaving group to form an alkyl bromide. So what I have shown here, that the lone pair of electrons on oxygen act as a strong base and they will react with the phosphorus tribromide, resulting in an intermediate. We carry out the reaction in presence of pyridine. Pyridine is a weak base and it will remove the proton from here, resulting in the formation of a bromophosphite group, which is a weak base. Hence, bromide anion can easily replace it, resulting in the formation of alkyl bromide. Here we have taken the example of ethanol, treated it with tribromophosphorus, and in the process we have got high yield of bromoethane. For synthesis of primary and secondary alkyl chlorides, thionyl chloride is a good reagent as the side products formed are gases. Reactions with thionyl chlorides are normally carried out in presence of potassium carbonate or weak organic base, that is pyridine. As you can see on your screens, alcohols react with thionyl chloride, resulting in formation of alkyl halide, sulfur dioxide and hydrochloric acid. This reaction gives high yields of alkyl chlorides since sulfur dioxide and hydrochloric acid are gaseous in nature and can be expelled from the reaction medium. So here we've shown the reaction of 2-octanol with thionyl chloride when 2-chlorooctane is formed in 81% yield. Similarly, if we carry out the reaction of a primary alcohol, that is 2-ethyl-1-butanol with SO2, SOCl2 in pyridine, we get 1-chloro-2-ethylbutane in 82% yield. If we look into the mechanism of the reaction, what we find is that thionyl chloride converts an OH group into chlorosulfide group that can be displaced by a chloride anion. Pyridine is generally used as the solvent in reactions of alcohols with phosphorus halides and with thionyl chloride because it prevents the buildup of HBr or HCl, and it itself is a relatively poor nucleophile. So if we look into the mechanism of the reaction, Here again, the lone pair of electrons on oxygen will act as a base and form a bond with the sulfur, which is sulfur of thionyl chloride, which is electrophilic in nature, resulting in the formation of a complex. Now, pyridine, being a weak base, will abstract a proton from this intermediate, converting it into a chlorosulfide compound. This chlorosulfide group is a better leaving group than chloride ion because it is a weaker base than chloride anion, and the chloride anion will push out this chlorosulfide group, resulting in the formation of alkyl chloride. Here I have demonstrated the mechanism of the reaction by taking an example of methanol. That is, methanol is treated with thionyl chloride. When we get a complex, from that complex pyridine pulls out a proton, resulting in a chlorosulfide group, and this chloride, being a strong anion, a strong base, pushes out the chlorosulfide group, resulting in the formation of methyl chloride. So now if we summarize the whole lecture, what we find is that tertiary alcohols give high yields of bromides and chlorides when they are treated with HBr or HCl, because tertiary alcohols result in formation of carbocations which are stable, hence they react easily with the bromide anion, resulting in the formation of the product. Whereas primary alcohols react with phosphorus halides or thionyl chloride, resulting in the formation of bromides or chlorides, that is, the bromides and chlorides of primary alcohols, because primary alcohols do not form stable carbocations. Hence, the reaction takes place in one step where the bond formation and the bond cleavage takes place simultaneously, circumventing the step which involves the formation of carbocations. In my next lecture, I shall be discussing the mechanism of nucleophilic substitution reactions, that is, bimolecular nucleophilic substitution reaction and unimolecular nucleophilic substitution reactions in great details with reference to alkyl halides. There, I shall also refer to the reactions which I have discussed today in order to make your concepts more clear and sound. Thank you.